someone sitting here? There's room here. There are a few empty seats. Okay, so let's start. So Happy New Year. If you didn't know, this is the first day in the Jewish New Year, so we're celebrating by continuing with CS 519. So hopefully most of you were here last time. We talked about what the class is about. This is just a quick reminder of what we're going to do in the class, and today we're going to start talking about learning. So, okay, so before that, a few administrative things. So we have a website. Please visit it frequently. I mean, we're going to announce things there. We're going to put the slides, videos, talk about the schedules and policies. We have Piazza. Not all of you are on Piazza. Please be on it. This is another place where we're going to announce things, and this is a good place for you to discuss things among yourselves. So office hours. So we're starting today. Check the schedule online. So people have asked me about Canvas. So Canvas is going to be used for homework, but other than that, everything is open. So everything is going to be on the website. So if you are on the waiting list, it shouldn't prevent you from following up on everything we're doing. This week, we are going to start also with the discussion sessions, the recitations. Next meeting, Wednesday, is going to be devoted to Python. And then we're going to follow up on this with details in the next two discussion sessions, which are going to be Wednesday afternoon and Thursday afternoon. Hopefully, all of you can make at least one of these. If not, let us know. We can still massage it a little bit. Check the website for times and locations. A couple other things that I think are of interest to you. So registration. So the class is still kind of full, even though when you check it online, it doesn't look full. Today we issued about 20 more permits. Anyone here got a permit today? Only one. Okay. When you do get it, who is on the waiting list here? Oh, many. Okay, so when you do get the permits, and you will get it in the next few days, please, as soon as possible, register so that we'll have a better idea of how many people are in the class. There are a few seats over there and better staircases on this side. So please register quickly. If you don't want to take the class, please withdraw quickly. And if you're on the waiting list and you decide not to take it, also do it quickly, because the time is short and many people are waiting. We're trying to monitor it daily and add people. One thing to remember is that homework 0 is mandatory. So if you are on the waiting list, do it. Follow the instruction on the website. We didn't issue the solution yet because we want everyone to do it. So you guys will feel more comfortable if you come down or go to the other door. Oh, someone is going to help you with that. Thanks. Okay. Questions? Yeah.
Do you know where the discussion sessions will be?
It's on the website. Yeah.
Well, the
Yeah, hopefully this is being recorded now, and it's going to be available on the website.
Oh, I meant for
The recitations are not being recorded, no. So if you cannot make any of these, let us know. I'm not sure that we'll be able to schedule it so that everyone can make it, but we're going to try. Other question, yeah. It's also on the website. So it's gonna be out in 2 weeks or something like that, maybe a week and a half. Homework 1, not homework 0. Homework 0 is out. Yes? So the quizzes are small things that should take 10 minutes of your time. The goal is to make sure that you know what we've done so far and that everything is at the top of your head before the Monday lecture. So if you listened and went over the lecture notes, shouldn't take more than 10 minutes. That's the idea. Otherwise, it will force you or encourage you to look at the lecture notes and so on. So it's really just a small thing. We're going to typically make it due Sunday night and maybe issue it on Thursday or something like that. Homework are going to be big problem sets that is going to take a lot of your time. I don't know how much, but I would say 15 hours. So there are going to be only 5 of these, and we'll discuss it when we see the first one. Other questions? Yeah. Are the quizzes in class, or? No, it's everything is online. It's going to be online. It's going to be graded automatically, so you'll see what happened. Yeah. More questions? Okay, so let's move on. Please feel free to ask questions as we continue about anything. So last time we talked about the badges game. Hopefully you remember. If not, look at all of the data online. I'm going to show some snippets of it. And this was our first example of the key learning protocol that we're going to cover in this class, supervised learning. So I gave you a list of names, some labeled plus, some labeled minus, and the puzzle was to try to figure out what is the model behind it, what is the rule that governs the labeling of the data. And we discussed a little bit some of the issues. The first question that I asked is, are you sure that you got it? For some of you that got it within seconds, we discussed why are you sure that you got it? And I think we converged to 2 issues. One of them, it was consistent with the data. But there are many things that can be consistent with the data, including the piece of paper itself. And the more convincing argument was that it's a very concise explanation for the data. And if it's so concise and it explains so much data, must be kind of true. And this is really an important principle in learning, something that we're going to quantify later in this class, but something that you want to keep in mind. And then we talked about a few other issues. So before I get to it, this is kind of like the data, a list of names with plus signs or minus signs. Here are 2 of them. In all cases, these were names that were taken from a conference that happened 20-some years ago, one of the first machine learning and computational learning theory conferences. And the question that we asked, what function was used to assign these labels? So hopefully the question is clear, simple. This is the fundamental question that we're going to ask this class. And then you can imagine that someone gives you test data. Some of these names actually appeared on the list, so you know the label. Some of them, Shivani Agarwal, wasn't on the list. But you can think about, okay, so what label should we assign her? And once you infer the model or induce the model from the data, you should be able to assign a label to it. Okay, so we discussed several questions. I'm not going to attend to all of these. Look at the red-colored questions. We asked which problem was easier, the problem that was posed to the people in the conference or the problem that I posed to you. And you agreed, I think, that I asked you an easier question. And again, think about why it was easy, because this is a fundamental question in learning. I basically told you or narrowed down the set of features that are important. I told you it's not the height of the person, it's not the shoe size, it's not their country of origin, it's something in the name. We talked about representation, another key issue that we're going to continue talking about today. What you see is a string. In order to even think about it computationally, you have to think about, how do I represent this? And as I said, we're going to touch upon this. And the final bullet that I want to highlight is background knowledge. You gave me a concept. Anyone remembers what was the rule? Second letter of the first name was a vowel. And then I pointed out, you can come around. I pointed out that vowel wasn't part of the input, at least not an explicit part of the input. So you had to bring some background knowledge in order to even represent this in a feasible way. Okay, so you can think about it, and you can think about an algorithm. This is where we stopped. Can you write a program that takes this data as input and predicts the label for your name or anyone's name? So this is something you want to think about still. And instead of thinking about the badges game, think about this problem, which I suggested last time. This is my email classification problem, much harder problem. Maybe you can come up with a way to do it that is doing a better job than Apple does. It's about 50%. So the problem here is the same problem as the badges problem. Given an email message that I got, decide which folder it should go to. So we're going to talk about it. So this is our representative supervised learning problem. And now we want to start moving toward an algorithm and address some of the issues, or at least introduce some of the issues that we're going to look at in this class. So we're talking about supervised learning. Why is it supervised? Because we start with input data, a collection of items, our input space, that we want to classify. And we start with a collection of outputs, labels, that we want to classify into. And we think that there is a function that maps these inputs to outputs. Right? So this could be email messages to a folder name, or it could be a name to a plus or a minus. So our goal is to find this function, f of x, or even more specifically, we just assume that this f exists, right? And our goal is to use machine learning methods to find this function. Now, if this mapping from x to y was trivial, we wouldn't have this class. We really care about these cases where just looking at the data, we don't really know how to program this mapping from x to y. We really need to develop other methodologies, methodology being machine learning, that is going to look at a lot of data and figure out on its own with some quotes around on its own, what is this function? So again, think about one of the examples that I've given, spam filtering, or another example which we talked about, the Christopher Robin problem. And all these are examples of that, right? So you give an input. In this case, you're given names of people in a story. And the question is, do they represent the same person? Yes or no? Boolean function. And in principle, the supervised learning protocol calls for, I'm going to give you a lot of stories with a lot of pairs. And for each pair, I'm going to tell you, yes, same person. No, not the same person. And eventually, you want to be able to find this function that looks at the two names in the context in which they appear and decides yes or no. And I think we agree that it's not an easy problem. Even for you, when you look at it at the beginning, it takes some time, and it requires a little bit of understanding beyond just looking at the string. Okay, so what is the protocol that we're talking about? So we're starting with some input. We're going to always call it X. Capital X is going to be the space of all inputs. Lowercase x is going to be an item. And we want to map it to a space of outputs, y. Lowercase y is going to be a specific label. And we assume that there is a target function that can do this. And it's a hidden target function. That's why it's dashed there. What we're going to do is we're going to try to learn a model, g of x. And hopefully g of x is going to be pretty close to f of x. And we're going to have to define what do we mean by pretty close. And this could be application specific. So in order to do this, we'll need a learning algorithm. This learning algorithm is going to take our training data. So this is where it becomes supervised, where I'm giving you the x's along with their labels y's. So a bunch of pairs, which is my training data. And out comes a learned model, g of x. So that's the game we're playing here. Of course, you can think about other learning protocols. Can you think about other ways to learn things other than this collection of pairs that I've given you? Yeah?
Supervised learning where you try to find pointers and make your own labels based on something similar?
So in this case, what will be the input?
In that case, the input would still be the training data, but it would be unlabeled, which is really like X1 dash.
Only the x's. So I'll get only the x's. But someone tells me that there is a collection of y's that can be associated with these x's, and I try to find it myself. Or it could also be something in the middle where some of the x's I'm given y's, and for some I don't. But I have some notion of x. This is the collection of possible x's. Not all of them I know the labels for. You can also think about a more interactive way of doing it. And the interaction could be in multiple ways. It could be, you give me x1, I'm trying to guess what is y1, and you tell me whether it's right or wrong. You give me another x, I'm trying to guess whether it's right or wrong. What is y2, and then you tell me whether it's right or wrong. Or maybe I can even guess g. After I'm looking at a few examples, I'm going to guess g. And you tell me, no, it's not the right g. Here is a counterexample. And I can keep on going. Yes?
How close does the learned model have to be to the target model to be considered correct?
I don't know. Good question. I don't even know what does close mean. We'll have to think a little bit about it, and we'll start thinking about it already today. But it's a great question, right? This is really one of the key questions we want to address. Maybe there's no hope of learning F exactly. How do we define success? Yeah?
How do we know that label data is not biased?
what is biased here?
So I mean, let's say the training data we have is not comprehensive for the subject you're trying to learn, and then it has a model which would not work in other cases. So it's really biased.
Yeah, excellent question. So I'm given training data. Maybe the data I'm going to see tomorrow on which I need to evaluate my model is very different than the training data. I guess that's what you mean when you say biased. Good question. In fact, the bottom line answer that we're going to give to this is if the training data is very different than the test data, we cannot do anything. I mean, we can learn something. It's not going to do well on different data, right? If all your life you've seen gray elephants and you see a white elephant, maybe you're not going to call it an elephant. So this is a kind of a paradox that philosophers that looked at induction talked about for years. And when we try to make a computational theory out of it, we're going to face exactly the same issues. Basically, what we can do is going to be limited to there is a distribution over the data. What we see in training has to come from the same distribution as what we see in testing. We're going to quantify these things a little bit better, but hand-wavingly, that's basically the issue. And you're right, it could be biased, and we have to deal with it. So all these are issues that we are going to talk about. But what we learn here, this g of x, this is what we're going to use later on. And if the later on data is different, g of x may not do as well as we want. Now, in test time, which is what you're asking on, we're going to have some labeled data, because otherwise we're not going to know whether our model is good or not. Not in the application, but as we develop the model, we need to have some labeled test data. We're not going to look at the y primes here. We're going to split it, look only on the x primes, run our model on it, and then try to see whether what we predict, the g of x prime, is close enough, under some definition of close enough, to the y's. That's going to be the game we're going to play here. And again, you can think about, is there a better way to use the test data? Yeah? Okay, so one issue is maybe there's some tuning that you want to do to G. You've learned it, but maybe there's some tuning parameters. Maybe part of this data you want to use as a way of tuning. That's one issue. Why do I even ask the question? The reason is that it's a waste, right? So I have labeled data here, and rather than training on it, I'm saving it on the side. Doesn't make sense, right? Because intuitively, the more training data I have, the better my model will do. And here, what I'm doing is something that is counterintuitive. I'm taking part of the data, and I'm not using it for training. So you may want to think about other ways in which I can use all my data and still be able to evaluate and tune. So we're going to talk a little bit about it when we talk about statistical evaluation and statistical significance. But basically, what I want to bring up now and make sure you think about it, a lot of applications that we mentioned and we haven't mentioned and that you have in mind or you haven't had in mind really are classification problems of the type I just introduced. Even when they don't look this way, like automatic steering, really at the bottom of these applications, there is a classification problem. Okay, and that goes back to the list of things that we're going to do here. So as I said, we're not going to talk always about algorithms, even though the algorithms are the heart of this course. But in order to introduce algorithms, we have to talk about some of the perhaps more important issues in machine learning, which have to do with learning protocols and with modeling. And that's really what I want to start talking about now. So there are going to be really three issues that we care about: modeling, representation, and algorithms. And I want to put this up, okay, before I get to it. So what do I mean by modeling? Given an application, how to formulate it as a machine learning problem. How to represent the data. This is going to be key. Which learning protocol to use? And specifically, you want to think about where is the data and the labels coming from. Representation, there are at least two issues we want to care about. So one is, what functions are we going to use to learn? What is the g of x that I mentioned before? What kind of functions do we want to put there? That's a representation of the function. Yes?
What do you do if some of your training data is mislabeled?
Okay, very good question. It will be mislabeled. And the bottom line answer, or the simplest answer, is we will develop algorithms that can tolerate noise to a great extent. So the fact that some of the data is mislabeled will not matter. But bring this question up again when we start talking about algorithms, and we'll see how they deal with it. I want to go back to the point of representation. So there are two things we need to think about how to represent. One is what functions are we going to use in order to represent our hypothesis. So you gave me a function for the badges game, which was a simple rule. If the second character of this is that, then do this. This is one way to represent functions. There are many other ways to represent functions. And you also need to think about how to represent the input. We didn't nail this down even in the simple case of badges. What is the representation of the input? And that's going to be very important. And of course, algorithms. And in algorithms, you already brought up a lot of these issues. What are good algorithms? How do we define success? How do we know that this algorithm is better than another? How do we know that this algorithm is any good? We need to think about generalization. I mentioned last time that really learning is generalization. We want to be able to behave well on instances we've never seen before. How do we know that we can generalize rather than overfit the training data that we've seen? We can do very, very well on the training data. Who knows what's going to happen on new data? And of course, the computational problems. We are computer scientists. At the end, we want to be able to compute efficiently. What are the issues that brings? So to be a little bit more specific, let's look at this example here and look at this question. So what is the instance space? The instance space is how do we represent the features. So here is my example here of classifying email. What do you want? How do you want to represent the input here? So this image is not going to be your input, right? So you want to encode it somehow so that your learning algorithm sees something that they can compute. What would it be? Yeah?
The text and the header is all mixed in one.
So what do you mean when you say the text?
So the main body without any space.
Without any spaces?
Without any space.
Can you read it this way, even? You as a human being? I doubt you can, right? If you drop all spaces, which means now you have one string of characters. This could be a legitimate input. The question is it a good input? For example, do you want to distinguish between the sender and the subject and the content of the message. Yes or no? You have to make a decision. Do you want to tokenize the input, actually, to say, this is a token, this is a token, this is a token, this is a token, rather than looking at it as one big string? You have to make a decision. Do you want to split it to sentences or not?
Maybe have a list of words and then assign a number to each word. As much as you can.
You can assign a number to each word. So let's assume you have a big dictionary of 1 million words, and you just index it. What are you going to do with the word its, it apostrophe s? You have multiple options. It could be a word in your dictionary. It could be 2 words in your dictionary. You have to decide. Any other suggestions? So maybe some tokens are more important than others, and you want to be able to know this somehow. Now, I don't know how to decide whether a word is a verb or a noun. This could take additional computation. You have to decide whether it's important to your representation or not. But at this point, the key thing I want you to think about is that even how to represent it is going to be important and something to think about. What about the label space? So the way I presented it here, I want you to map this email into folders. So what is the label space? The set of all folders. But you can think about whether you want this to be a flat set of folders. Maybe you want it to be only the folders that were touched over the last year. Maybe there is a hierarchy of folders, right? The set of folders could be a tree, and maybe you want to represent it as a tree because it makes some sense. So even the label space could have some structure. What is the hypothesis space? By hypothesis space, we mean what kind of functions are we learning? What kind of functions do you think could be useful for mapping a set of email messages into into folder names? Give me a suggestion of a function. Yes?
Maybe a linear function that takes in the first, so if you split, like you tokenize all the words and then every word has a weight. So you linearly can do that based on the weights.
Okay, so I could assume that my input is just a list of tokens, and somehow I assign weights to these, and then I'm going to sum up the weights, and if it's greater than 75, I'm going to say this folder. If it's less than 75, I'm going to say that folder, something like that. But I have many folders. I have 100 folders. So this is a good idea to use a linear function, but I have to do a little bit more if I want to do it into 100 folder rather than just one of 2. Yeah?
You could use that approach, but instead of deciding this folder, that folder, you could that function for every folder that decides kind of a score and how likely it is to be in that folder.
So each folder will have its own function, and it will ask, is this my email or not? And then you'll compete. The folders will compete on each email message. The one that wants it most is going to take it. This will be a winner-take-all policy. I'm surprised that none of you says something like, here is a simple classifier here. If the sender name has a folder named after it, him or her, put it there. That's going to do it for a lot of foldering schemes, right? Filing schemes. Much simpler function. just a rule. Maybe multiple rules. Maybe that's going to be the first rule. If the sender has a file name after it, put it there. Otherwise, do something. Maybe a few other rules, maybe a linear function. But you can already see that there could be many functions. No one suggested a neural network, but a linear function is a neural network, so that counts maybe. Which learning algorithm to use? So you have to decide what is your hypothesis space, and this will at least narrow down the set of learning algorithms you can use, because different learning algorithms will use different representations. And the other question is, what is the loss function? You ask the question of how close is it? So we're going to quantify this using this notion of a loss function. So I have the truth. I know that these emails were supposed to go to these folders. I have the prediction of my model. How do I know? How do I quantify how good it is? Suggestions? Yeah? So basically, so I haven't placed them yet. I just want to know which folder name was assigned by my model to each of the emails. So how do I know whether my model was good or not? How do I quantify the performance? Yeah? So just count how many disagreements are there. That could be a good function, a good evaluation. Is this the only one? Yeah.
I think that would be a problem because if you have, let's say, two folders, and one folder gets a lot more email than the other one, and you're trying to classify it, if one folder that has a lot of emails, you may get a lot of corrects, but if the folder that has a lot less email, you may get a lot more. So
Right. Yeah, excellent. So maybe I do have some preferences. Maybe I'm willing to make one-sided mistakes. I want my model to abstain if it's not sure, and to choose a folder only if it's almost 100% correct. So I care about weighted type of mistakes, not just counting the number of mistakes. I could think about, I suggested before that the filing system could have a hierarchy. Maybe I want to take the hierarchy into account when I measure my loss. So let's assume I have a tree and it has two parts: school stuff, non-school stuff. Within the school stuff, it's okay if it moves from one folder to the other, but I don't want school stuff to move to the non-school stuff and vice versa. So I want to penalize more if it's moved from one side of the tree to the other. Within each subtree, I don't care so much. So do you see the difference in this loss function? So I'm not going to count only mistakes. I'm also going to care about what mistakes are happening. So these are different loss functions, and these are going to drive the way we develop a learning algorithm in different ways. Because some learning algorithms will just be trained so that the total number of mistakes, say, goes down or is minimized. And in some cases, I will care about other issues. So all these are things that we want to talk about as we go forward. They will drive our machine learning algorithm. So let's talk in a few more details about these issues. Instance space. I already mentioned a few of these issues. We can represent the instance as features, a collection of Boolean features. Boolean means yes or no. For example, is there a folder named after the sender? Maybe this is a feature, an important feature. Does the email contain the word class? Maybe it's important. Does the email contain the word waiting? Maybe it's important. Does the email contain the word class and the word waiting? Is there any difference between the first line 2 and 3 and line 4? Or is it just, or is line 4 redundant? Yeah?
Both in the same email might mean a different thing than just one of them.
So in some sense, line 4 is more expressive than each one of line 2 and 3. Now, if you know the truth value of 2 and 3, you also know the truth value of 4. But we will see even today, hopefully, that there is a notion of expressivity of the hypothesis space, of the functions in the hypothesis space, for which this actually makes a difference. Whether you require both of them to be on, both waiting and class, or just one of them, and maybe also the other. So this is one way to represent it as Boolean features. You can think about numerical features, right? So you can say, how often does the word learning occur in the email? Or how long is the email? Or how many emails have I seen from this sender over the last day, week, month? These are numerical features. Maybe they are important. Maybe I don't want just to classify based on this specific email, but I want to know something more. Yeah?
You could also have a function that varies as you populate your folders with more emails. So maybe it compares the set of all the words in the folder already, and then compares this email to all of that. So then you don't have to brainstorm. Well, I think it would be class and waiting. You can compare, what were all the emails last year, and what are they talking about? What's that categorized this year?
So, yes, very good. So the question is, at what stage in my algorithm or in my process do I look at previous emails? Do I look at it at the stage where I decide what to look at? Or do I look at it at the stage of, I already have a representation for each email, or maybe for the collection of all emails, and this is input to my learning algorithm. I allow my learning algorithm to also look at the history, and in fact, I allow my learning algorithm to look at the history in a specific way. For example, by counting words, but not in other ways. So I allow it to take some statistics over previous data. So all these have to go into the representations that I care about. And you can also think about simpler representation. This was suggested before, just bag of tokens. Just list each email representation is the list of all tokens that appear in it. That's it. In this case, I don't represent history directly. I have to decide still what are tokens. May not be so simple. I mean, we'll add some noise to your representation, but basically the point is you understand that we have to think about representation. You can take, again, the example of the badges game and see that there are many, many options. Okay, so once we decide, let's assume we decided our collection of examples, capital X, is going to be an n-dimensional vector space. Say R to the n, where capital N here is the number of features, the dimensionality, or 0, 1 to the n if we're dealing with Boolean features. Each dimension will correspond to one of the features. Is the word class there? Yes or no? And then we're going to get a feature vector, which is a vector of all the features. This x, which is x1 up to xn. So really what I'm working on with is a vector space of a lot of examples. All I show here is 2 of the dimensions. I don't know how to plot a lot more than 2. But each example, each email message, if you want, is a point in this space. It's important to realize that good features or good representations are essential. the success or failures of your algorithm will depend on your representation. So think about the badges game. If you were looking in the wrong direction, looking only at the height of the person, you'll just not get it. If you don't represent the information, you just won't get it. And of course, we are not going to teach you in this class what specific features are important for your application or application area. We're going to try to talk a little bit about some general principles. Label space. Again, we talked a little bit about this before. We can think about categorical feature spaces, binary classification, or multi-class classification. Binary classification is the badges problem, plus or minus. Multi-class classification is my email problem, which of the 100 folders. You can think about structure object, sequence of labels, parse trees. You can think about this example here. So I have an image, there's a cat there, but what I care about is not whether there is a cat or not, but rather I want to understand parts. Where is the head, where is the neck, where is the torso? So I really want to segment it and understand which part where it is. So I could make it a binary problem by looking at this blue square and red square and ask, where is the neck, the blue or the red? But more generally, I care about the structure here. I care about classifying all these components together because they are not independent. Right? So if I know where the head is, where the neck is constrained a little bit. Similarly, in the text problem on the right, you can see this is a temporal relation problem. I have 3 events that I care about, meeting, leaving, Thursday, and I want to know the order. What is the temporal relation between them? In this case, I want to know that the meeting happened before leaving, and leaving happened included in Thursday. So again, I want to make multiple decisions at the same time because they are not independent decisions. We're not going to talk a lot about structured learning in this class. We're going to talk mostly about binary or multi-class decisions, but there are others that we're going to hint upon. So sometimes the output labels are going to be numerical, regression. In fact, most of our algorithms are going to output real valued numbers. Most often than not, we're going to care only about truncating them, deciding whether it's positive or negative, but still they're going to output real valued numbers. You can also think about ranking of objects, and the labels are going to be ordinals. You care about whether f of x1 is larger than f of x2. You don't care about specific numbers. So labels, and as I mentioned before, the label space could be hierarchical, and you may want to care about this too. And finally, we want to get to the model, which is perhaps the most interesting part. We need to decide which kind of model we want to learn. So let me start with the following example. This is a learning problem. I already solved the representation of the input. I have features, in this case only 4 features, x1 up to x4. I know that there is a function, f of x1, x2, x3, x4. It's just unknown to me. It exists. And I'm giving you examples. So at this point, we don't care what x1 represents, what x2 represents, and so on. They are Boolean features, and I gave you the label. So we know that the example 0010 has label 0. The example 0100 has label 0, and so on. And the question is, what is the function? That's the learning problem. Suggestions. Yeah.
If you take the sequence of 4 as a binary number, why returns 1 if it's odd, and
Okay. If the number is odd, it's, if there is 1 in the X4 place, doesn't work. Okay, but good direction. So let's try another suggestion, yes? Okay.
The observation is that lines 3 and 4, you have the decimal 3 and 9, you have 3 to the 1.
Okay, so you want to say that the positive examples are those that satisfy what?
That they are, the positive examples are some 3 to the n.
Okay. 3 to the n, so it's either 3 to the 0, we don't know, 3 to the 1, which we know is a positive example, 3 to the 2, which is 9, which is a positive example, and so that works. 3 to the I, where I is an integer, is positive. Good function? Not good function?
We can't possibly tell.
Okay, we can't actually tell, but for the training data, does it work? Any other suggestion? Yeah. Okay, x4 and not x2. Let's see. So if x4 is on, which happens in 3, 4, and 7, but x2 is not on, which happens in x3 and x4, then it's a positive example. So that works? Which function do you like more? Are they the same function? So let's see. So the problem with the first function is that what is the domain of this function here? So how many input? You said we don't know because there are so many possibilities and you only gave us 7 examples. How many inputs are there? Altogether. So I have 4 features, right? x1, x2, x3, x4. They are all Boolean features. So how large is my instance space here? 16, right? So I have 16 options. That's it. 2 to the 4. And out of the 16 examples, I gave you 7. You don't expect me to give you all 16, because then there's no learning problem. If I gave you all x, right? So I cannot put, in interesting problems, instead of 4, you'll have 100, and then you would agree with me that it doesn't make sense to list 2 to the 100 examples. You'll never see them. So I'm just scaling down a little bit. So here there are 16, I gave you 7 out of them, which is actually a large fraction of the input space. Now, this is all of the input space, right? And for 7 of these 16 examples, I've given you labels. Now, we already have 2 functions that are optional here. Are there other functions? Could you imagine other functions that you can learn in this case. Yes?
Well, you've added some additional information here, because the way you ordered it implies that it's linked to binary, because that's how you counted all 16.
No, no, not at all. It was always 16, irrespective of how I write it. Right? I told you that the xi's are Boolean features, so there are 16 inputs. The fact that I sorted it one way or another does not have to be meaningful to the function at all. I just have to write it one way or another, and this was my way to make sure that I didn't miss any of the 16. So doesn't have to be related to the function. But are there other functions? Yes?
Yeah, you could have x1 or x3 and x4.
X1 or X3 and X4, that's also true. So X1 or X3. So for example 3, it works. For example 4, it also works. And that's it. So here's another function. Is it the same function of any of the other two? No. So what do you think? Are there other functions? Yes?
You might be assigning weights to the factors. So like for the first, it might be positive for the first and the fourth, there might be positive weights, and for the second and third, there might be negative weights. And so I've come with some ways, but I'm not sure whether it works with the other 11, other than but it works with the 7 example.
Okay, so you have another suggestion. In fact, each one of you can have multiple functions, and we're still not going to exhaust the number of possibilities. So let's think a little bit about it. There are 16 inputs here. And I'm looking for filling the question marks on the right? How many question marks are there? 9 question marks. So altogether, how many functions are there? Each question mark, I can put a 0 or a 1, right? So altogether, how many combinations do I have for functions here? Yeah? 2 to the 9, right? So I can put, instead of the first question mark, I can put 0 or 1. Instead of the second, I can put 0 or 1. All the combination is the product of this. So there are 2 to the 9, 512 different functions, right? So in general, on 16 inputs, there are 2 to the 16 functions. Think about it. For each input, I can decide to make it 0 or 1, right? And therefore, there are 2 to the 16 options. When I change one of the y's, I change the function. Everyone agrees that there are 2 to the 16 functions over 16 inputs? Boolean functions over 16 inputs. In this case, I limited it because I gave you 7 already. It leaves us with 2 to the 9, which is a large number still when we're talking about this small scale problem, 512. So each one of you could have chosen 3 different functions and would still have some function to spare. You gave me just 3 or 4 representatives, and what does that mean? You were right at the beginning. We cannot tell. I gave you only 7 examples. There are so many options. So what are we talking about here? Is learning even possible? Maybe we can close the class and that's it. Suggestions?
Say you can try to look for patterns and then identify the simplest explanation.
Okay, so simplest is a keyword here. There was a suggestion that I have the simplest function, and maybe you're right, maybe it is the simplest function. But what has to be clear is that learning as is on this slide is ill-defined. It's not possible. It's not possible unless you make additional assumptions, because I just gave you a small sample of the input space, the instance space, and there's a huge number of functions that could be consistent with this. And from the perspective of consistency, they're all equal. All of them agree with this data, right? So how do we choose? So the key concept has to be that of hypothesis space. We have to introduce some constraints on the output. We're going to say, you know what? I'm not going to consider all 512 functions. I'm going to have some biases. Simplest comes from this family, can be represented this way, or something like that. With this, only with these biases, we can make learning well-defined and doable. So I'm just putting it here so that we'll make sure, this is a very simple example. Nevertheless, it's an important example. So the counting problem, just to make sure that you all got it. So we talked about the fact that if we have a space capital Y, of size capital Y's, and my domain, my instance space is of size capital X, there are Y to the X possible functions. Too many in this case. So we have to consider a subset of the possible functions to make learning feasible. And this subset is something that we're going to call the hypothesis space, capital H. And capital H is going to be a subspace of Y to the X, space of all functions from X to Y, typically a very small function of this. Because when we were talking about 100 dimension in the input or 1,000,000 dimension in the input, the size of the number of possible functions is going to be too large to even consider. Okay, so let's think about hypothesis spaces. I can invent a hypothesis space. Here is a simple family of functions. All conjunctions, we know now what conjunctions are because you did homework 0. And is a conjunction. All conjunction of some size, 1 or 2 or 3 or 4, or maybe 3. I don't care about 4. So functions could be something like this, xi and xj and xk, where ijk could be 1, 2, or 3, or 4. There are 16 functions like this, and I can try and say my learning problem is choosing a function that is consistent with my data and is part of this family. I can try, doesn't work. So the notation I'm using it here is the following. I'm giving you the function, and I'm giving you the counter example that shows that this function doesn't work. So go over it if you want. It doesn't work. The same thing is not going to work also for simple clauses or simple disjunction, x1 or x3 or x4. Not going to work. So maybe I'm going to go to a more expressive class of functions. I'm going to define a more expressive class of function. It's going to be called M of n rules. So what do I mean by M of n? Y is going to be 1. The label is going to be 1. If and only if at least m out of the following n variable is 1. So here I'm giving you another table. My notation is as before. So this example, 2 of means 2 variables from the set on the left are on. And the value that I put in the table is the index of the counter example. So for example, you can look at this function. Okay, this doesn't work here. Oh, here. Let's look at this example. My set is x1 or x3. If one of them is on, I claim that y is 1. Doesn't work, example 1 contradicts it. 2 of them are on, that is both x1 and x3 are on, example 3 contradicts it. If you look at this example here, x1, x2, x3, if one of them is on, example 1 contradicts it. If 2 of them are on, example 3 contradicts it. So I can try to learn a function in this space of functions. There are 32 functions like this. And I've written all of them here. It turns out that one of them works, the one with the 3 stars. So the function here is 2 out of x1 or x3 or x4 are on. I put the 7 examples at the top right there. You can check that if 1 of x1, x2, and x4 is on, the example is positive. Now notice that this is a different function than any of the functions that you proposed, which shouldn't be a surprise because there are 512 different functions. Some of them have a concise description as this. Some of them will not have a concise description. But the basic idea I want to convey is that finding a consistent hypothesis is easy. There are many functions that are consistent with this. You have to make sure that you make some assumptions. And if this example is too simple, because I'm just talking about Boolean function, I'm just talking about 4 inputs and so on, and you were expecting to see that, we're going to do some neural networks here, don't worry, because this is a neural network. The function that I just described is really a neural network. In fact, all the functions that you described are also neural network. It's just a linear function of the input, in fact, all these functions. We're going to show this probably next time. But the important thing, this is just a joke, or supposed to be a joke. The important thing is that we found a consistent hypothesis in our hypothesis space. And I want you to keep in mind this concept. So what is learning then? So you can think about learning really as the removal of the remaining uncertainty. I gave you a few examples. If we knew that the true function comes from this family of functions, say m of n functions, then we can use the training data to choose the specific member in this family that we like. So learning always requires guessing a good hypothesis class. And we could be wrong. You suggested other functions that could be as good, but there are other functions. What does it mean that there are other functions? It means that there is at least one input on which they disagree. I don't know if you care about this input. I don't know if you'll ever see this input. But it's important to realize that these are different functions. So that's really learning. And that dictates general strategies for machine learning. So we can either think about a flexible hypothesis space, something that really can represent all functions. And as you see more and more data, you try to adapt to it. So decision trees, that is going to be the first or the second learning algorithm we're going to talk about, is a very expressive class of function. It can represent all Boolean functions, for example. You'll have to think whether you want to use it. There's going to be some caveats to using it. Neural networks, in principle, can represent all functions. Again, under some conditions, you want to think about whether you want to use it and how. Or nested collections of functions. So maybe you grow your collection of possible functions that you're willing to consider with your data and with failures to be consistent or almost consistent with the data. You start with one, doesn't work, let's grow the function space and keep on doing it. And the reason you may want to do this is because we like simple. You already got this intuition, and you like simple functions. And we're going to justify that simple functions are good, so we don't want to start with something that is way too expressive. You can do this. You can also start by developing representation language for restricted classes of functions. And sometimes this is useful. Sometimes you want to be able to say, well, I'm going to define some grammars, and this is going to be my representation. I'm going to represent things this way. Or I'm going to have some family of stochastic models, probabilistic models, and I'm going to learn into this representation because I think this is going to be expressive enough for my purpose. All these are biasing the space of functions you're allowing your algorithm to use. And as this simple example illustrates, it's important. Of course, once we have it, we're going to try to develop algorithms that fit the data. Fit is exactly the notion of how do you know that it's close to the hidden target function. We're going to discuss this and hope that if we fit the data or almost fit the data, we're going to do well in the future. And again, this is something that we'll have to quantify. Yes?
I have a question about in terms of terminology. Like, are we using hypothesis and functions like interchangeably, or are they?
Yes. Function. Hypotheses are functions. And I'm using hypotheses when it's the output of the learning algorithm.
So on one slide, it says hypothesis is a subset of possible functions.
Right. So hypotheses are functions. I'm going to define a hypothesis space to be a set of functions that is the subset of all possible functions. It will be the set of functions that my algorithm can deal with, or that I want my algorithm to deal with. So hypotheses are functions, and I'm going to use hypotheses when I'm talking about the possible outputs of my learning algorithm. So thanks, this is important. Okay, so going back to this categorization that I gave, what are we going to talk about? Modeling, representation, and algorithms. I'm going to start now next time, with a specific example where we're going to actually go through all this and finish next time with developing a learning algorithm that in fact is going to be a very general learning algorithm that we're going to see throughout the class. But we're going to start it with an example of something that fits here. Questions before we end? Okay, so next, on Wednesday, we're going to devote the class to Python. As I said, we're going to continue with this on Monday.
You're saying that you're going to like define a hypothesis space and restrict like what you're looking for technically. How is that really like learning? Like, because you're trying to search for something which you already like thought about. Like you're trying to go towards a goal of some sort of function, right? Is that like, for example, like the elephant example, right? Let's say you restrict your hypothesis space for colors of elephants to be white, gray, and like yellow. What if there's a red elephant and you've not included that in your hypothesis space? Then you'll never learn there is a red elephant. Yep. So isn't that bad? Shouldn't it always be general?
So my example here showed that you cannot be general. I mean, there are just way too many functions. You cannot explore all the space of functions.
Okay.
You have to constrain somehow what you're searching for. So the example of the elephants is a little bit trivial because it's only the label, it's not really the function, right? I didn't talk about, I don't know what is the function that maps an image of an elephant to the name of the elephant, right? So I think we're confusing here a little bit the label space and the hypothesis space. But there's no way beyond constraining the hypothesis space somehow. Either you do it algorithmically, as I said, so you say, I'm going to deal with all possible functions in decision trees or neural networks, but algorithmically you actually don't. Or you do it more explicitly, you just restrict the space. So think again about the problem of the 4 bits.
Okay.
And hopefully you convince yourself that there's no other way.
Okay. Okay. Cool. Thank you.
Professor, so kind of been trying to make this. You told me to talk to you because I don't know if it's I have to who went on the waitlist. It's my last semester.
Did you send me
Earlier I did, but you told me to talk to you. Now Nick told me.
Are you on the waiting list?
Yeah.
So drop me another email.
Yeah.
So I'm also on the waiting list. I haven't gotten an email yet by today because I said that's more time. You think that there's still a chance that I'll get in?
We're going to take a couple dozen place. People are working with class and people are working from the waiting list. So I can't say specifically for you, but yeah, we're going to take it.
That's all I need to know. Thank you.
Question, I want to register. I registered a few months back on the wait list. Still haven't gotten a permit.
So as I said, if all of you are asking about waiting list, so it's moving. I can't say anything beyond that. So if you didn't get a message today, hopefully you will. We just have to see. So a few of the people that get permits do not register, so we have to wait a little bit and then move down the waiting list. So there's still time. So what I suggest you do is just keep following the class, follow the webpage. There's nothing beyond homework 0 that you all have to submit. There's nothing now that you'll have to do. The first issue is going to be with quiz 0, with quiz 1, that we're hoping to be at the end of this week. But it's only half a point, so we'll be able to deal with it. So that's all I can say.
Regarding homework 0, if you missed the deadline,
Send it.
I'm sure about
Send it. Okay. Yeah. So we'll put it on the website. Yeah. Please send it because once you get into the class, you have to do it. So just send it now. It will also give you an idea of whether you want to be in the class or not.
My question actually, I'm registered for the class, but I can't make either of those sessions.
Okay.
I have class until 4:20 on Wednesdays, and I have class beginning at 5 on Thursdays. Both I don't think I can really miss.
Okay. So okay, drop me an email. I want to see how many are like this, and we'll try to adjust.
Thank you.
What's your name? I think actually. No, I think that means you should register.
Actually, this open status and pendant touches only for CS Corona and graduate.
No. You
There's no CS
you got this morning a permit.
I got a permit available mail, but I didn't have permit issued mail. It's like
I'm not sure what's the difference. Ask Nick about it. I think that means that we allowed you to register for the class.
but then I think that
So I think the 419, 519 issue, we can toggle them. I mean, I don't care how many are 419 and how many are 519.
okay, I think I talked to you.
Yeah, okay.
Thank you.
Hi, I have a few questions. One of them is, so homework 0, I already submitted it, but I realized that I have to do latex like 20 minutes for the deadline. So it's in latex form. I'm going to start doing latex.
Do it in latex again.
Again.
Yeah. I mean, no one will read it if it's in So you registered for the class?
I was part of the class. I did the homework, but then I realized that it's the first time I'm doing latex.
So we gave you a LaTeX template together with the homework, so it's going to be easy and it's going to be good for you.
It's like with the homework? Like it's like
Yeah. So we gave the LaTeX of the homework itself. So you can just follow it. It gives you a LaTeX template.
So is it okay if I like send it like later this week?
Yes, you can, when you email it, tell Dan that you already submitted it, but it wasn't related to the translating.
Other question I had was, so how do you make sure in a training the data is comprehensive for like a general? Is there anywhere to know if the data
It's not clear what does it mean for a general form.
Is there any type of trend you need to have, like in terms of like distribution? Does it have to have like a...
As you could see from the numbers that we showed today, it will never happen, right? So, in general, and now in specific applications, maybe you can talk about it in a better way, but if you think about an instance space with 1 million features, there are 2 to the million different inputs. You'll never see even a tiny fraction of them, right? So in no way you can talk about representing the space. So you really care about the specific distribution over the space, and you hope that from the support distribution you get so really the key issue is not so much how much you get, but rather what is the relation between, so there is a distribution over the instances, we're going to talk about it, and you hope that the training data is sampled from this distribution, and the test data is sampled from the same distribution. Under these assumptions, you can say something. That's basically, with a few other, tiny issues, that's basically the only thing for which you can say something. So we're going to get to it.
I forgot my last question.
Okay, next time.
Oh yeah, I asked this